Hello everyone, welcome to Enviro Pioneers. In this video, we will learn about thermal infrared remote sensing, a technique that allows the sensors on the satellites or the aircraft to detect the heat emitted from the objects on the earth. We have divided this topic into two parts. Part 1, it covers the basic concept including how the thermal sensing work and what makes it different from other remote sensing methods. And in part 2, we will explore the thermal behavior of different surfaces and learn the practical applications of the thermal remote sensing. Let us start with the definition of the thermal remote sensing. So, it is a branch of remote sensing that deals with the acquisition, processing, and interpretation of the data which is acquired primarily in the thermal infrared region of the electromagnetic spectrum. It also comes under the passive remote sensing, but it is different from the optical remote sensing because here mainly the radiation which are reflected from the earth surface is measured. But in the thermal remote sensing, we are mainly focusing on the radiation which are emitted from the surface of the earth. To understand the concept of the thermal remote sensing, we should know the difference between the kinetic temperature and the radiant temperature. All the objects in the real world having a temperature above the absolute zero, that is 0 Kelvin or minus 273.16 degrees Celsius, they exhibit random molecular motion. This molecular motion, it depends on the phase of the medium as well as the temperature of the medium. As we can see in this demonstration, we have the restricted movement of the molecules in the solid medium, while in the gaseous medium we have the free unrestricted movement of the molecules, and we have the intermediate movement in the liquid medium. And within a particular medium, this molecular motion is affected by the temperature. As the temperature increases, the molecular motion it increases. As we can see in the first case, here we are having the temperature up to 5 degrees Celsius. In the second one, here we have 20 degrees Celsius, and here the temperature is 40 degrees Celsius. And we can see that the molecular motion it increases as the temperature of the medium increases. Similarly, we can see in this animation, the movement of the molecules in this liquid medium, it increases as the temperature is increased. So the energy of the particles of the molecular matter in the random motion, it is called the kinetic heat, and it is also referred as the internal, real or the true heat. And the amount of this heat can be measured in the calories. The concentration of this heat, which is also referred as the true kinetic temperature, it can be measured using a thermometer. So, for this, we require the in situ temperature measurement, which can be done by placing the thermometer in the direct contact with the physical objects. During the molecular motion, when the particles collide, they change their energy state and emit the electromagnetic radiation. And because of this, an object's internal kinetic heat is converted to the radiant energy. This radiant energy is also referred as the external or the apparent energy, and it can be measured using the remote sensing. So, the electromagnetic radiation which is exiting an object is called the radiant flux. That is the total amount of radiant energy emitted per second in all the direction, and it is measured in watts. And the concentration of the amount of radiant flux exiting from a particular object is its radiant temperature. So, the kinetic temperature is the concentration of the kinetic heat, and it can be measured only with the help of the in situ measurement using the thermometer, and the radiant temperature is the concentration of the amount of radiant flux, and it can be measured using the remote sensing. For real world objects, except those composed of the glass and metal, a high positive correlation is found between the true kinetic temperature of the object and the amount of the radiant flux which is radiated from the object. Now, with this concept, if we measure the radiant temperature of an object by placing the radiometer at some distance from it, the radiant temperature would correlate well with the object's true kinetic temperature. So, this is the basis of the thermal infrared remote sensing temperature measurement, but the remote sensing of the radiant temperature is always less than the true kinetic temperature of the object, especially for the land surfaces, and is due to the thermal property called emissivity. So, the radiant temperature of an object depends on the kinetic temperature as well as the emissivity of the object. We will cover emissivity in more detail in the latter part of this video, and the kinetic temperature of any object depends on two main parameters, heat budget and the thermal properties. So the thermal properties are associated with that particular object. In this we have the thermal conductivity, specific heat, heat capacity, thermal diffusivity and the thermal inertia. And the heat budget at any particular place depends on the solar heating, long wave upwelling radiation, long wave downwelling radiation, or if there is anomalous heat sources. And the solar heating, it depends on the solar elevation, cloud cover, atmospheric condition, and the topographic altitude. These we have already covered in the first four videos of the remote sensing and the GIS playlist, and this we will cover in the next video, that is the part 2 of the thermal infrared remote sensing. The primary source of energy for our earth is the sun, and the solar radiation is mainly the shortwave radiation. And when this radiation it enters into our earth's atmosphere, some portion is reflected by the cloud and some gets absorbed in the atmosphere, and the rest which reaches to the earth's surface, depending upon the object on which this solar radiation is incident, it can either be reflected or it can be absorbed. So the energy which is absorbed by the earth's surface, that is emitted as the electromagnetic radiation having the longer wavelength. अब ये जो लॉन्ग वेव emitted radiation है, that may get absorbed by the greenhouse gases in the atmosphere, and the energy which is absorbed in the atmosphere, it may get re-radiated back towards the earth surface, or it can be emitted towards the space. So some of this emitted longer wavelength radiation which passes through the atmosphere, it can be recorded using either the airborne or space based thermal infrared detectors. I would request you to please go through this particular video, that is the terrestrial radiation and energy budget of the earth, just for your reference. Here we have also discussed the difference between the short wave and the long wave radiation. The emitted long wave radiation from the earth, it lies in the infrared portion of the electromagnetic spectrum, and this infrared it ranges from zero point 0.7 to 1000 micrometer, and it can be differentiated into near infrared, short wave infrared, mid wave infrared, long wave infrared and far infrared, depending upon the wavelength range. As this IR band extends from zero point 0.7 to 1000 micrometer, in the remote sensing, this wide band is divided into two major components. The reflected IR band that ranges from zero point 0.7 to 3 micrometer, and the emitted IR band that ranges from 3 micrometer to 1000 micrometer. So this represent the thermal radiation or the heat energy that is continuously emitted by all the objects on the earth surface. So as we can see here in the passive remote sensing, we have the visible and near infrared remote sensing, which measures the reflection intensity in the visible and the NIR portion of the electromagnetic spectrum, while the thermal infrared remote sensing, it measures the radiation intensity, that is the energy emitted from the earth surface. If we see the satellite data of Earth for the reflected solar radiation and the emitted heat radiation, we can see the difference. Here the range is from 0 to 700 watt per meter square, while the emitted heat radiation, here the range is only from 0 to 350 watt per meter square. because most of the earth's emitted long wave infrared radiation, it is absorbed in our atmosphere by the greenhouse gases like the water vapor and the carbon dioxide, and because of this only a portion of infrared energy is transmitted from the terrain to the detector. So this range of infrared spectrum which get transmitted through the atmosphere is referred as the thermal infrared atmospheric window. Atmospheric window is the range of electromagnetic spectrum which passes through the atmosphere without much attenuation. You can refer to this particular video for more detail. So now coming to the thermal infrared atmospheric window, as we can see here on the y-axis we have the atmospheric opacity, while on the x-axis we have the wavelength. And if we see for the infrared portion, that is from zero point 0.7 to 1000 micrometer, we can see that most of the infrared spectrum is absorbed by the atmospheric gases, and there is only selective wavelength ranges for which the satellite based remote sensing can be done. So in the remote sensing, instrument can be used to detect the infrared energy only in these two regions, that is the reflective infrared region that ranges from zero point 0.7 to 3 micrometer, and in the thermal infrared it is from 3 to 14 micrometer. As most of the emitted IR radiation is absorbed in the atmosphere, and water vapor, carbon dioxide and ozone, these are responsible for most of the absorption. And within the thermal infrared region, there are two most effective atmospheric window, 3 to 5 micrometer and 8 to 14 micrometer, because as we can see here that this particular wavelength range, that is 5 to 7 micrometer, that is getting absorbed in the atmosphere by the water vapor molecules. So, in thermal remote sensing, the electronic detectors can be engineered to be sensitive to the photons of the thermal infrared radiant energy exiting the terrain in the two primary atmospheric window, that is 3 to 5 micrometer or 8 to 14 micrometer. So when we are using the suborbital platform like the aircraft, in that case both the spectral bands can be utilized, but in the orbital or the satellite thermal infrared remote sensing, this 3 to 5 micrometer region is more challenging due to the interference from the solar reflection in the daytime imagery. Therefore, the 8 to 14 micrometer window is widely utilized for the thermal remote sensing application. Now, within this window, the electromagnetic radiation falling in 9.2 to 10.2 micrometer range, that is absorbed by the Earth's ozone layer. So, within this window, we have the range from 8 to 9.2 micrometer, and then from 10.2 to 14 micrometer. Now let us learn about the thermal radiation laws which are important in the thermal remote sensing, because this branch deals with the emitted energy from the object. We will start this with the definition of a black body. So a black body is a theoretical construct that absorbs all the radiation that falls on it and radiates the energy at the maximum possible rate per unit area at each wavelength for any given temperature. In the nature, no objects are true black bodies. However, we may consider Sun as a black body having the temperature of 6000 Kelvin and the Earth as a black body having the temperature of 300 Kelvin. Suppose if we use a sensor pointing towards a black body, we would be able to record the quantitative information about the total amount of radiant energy in the specific wavelength as well as the dominant wavelength of the object. Theoretically, these two information can be determined by these two laws, Stefan-Boltzmann law and the Wien's displacement law. So let us see about these laws. So first is Stefan Boltzmann law, which states that for an ideal absorber or emitter or a black body, the total spectral radiant excitance, that is the energy radiated per unit surface area per unit time, this is directly proportional to the fourth power of the black body's temperature. and is represented by this formula. M is equal to sigma T to the power 4. M is the total spectral radiant excitance and sigma is the Stephen Boltzmann constant, and its value is 5.6697 into 10 to power minus 8 watt per meter square per Kelvin to the power 4. In this graph, on the y-axis we have the radiation intensity, on the x-axis we have the wavelength. And these four curves, they represent the radiation intensity for the black body having the temperature 5000 Kelvin, 4000 Kelvin, 3000 Kelvin and 2000 Kelvin. And the area under the curve, it represents the total amount of radiant energy across the wavelength range. And we can see that as the temperature increases, the total amount of radiant energy, that is the area under the curve, it increases, and the radiant energy peak, it shifts towards the shorter wavelength, means towards this side. The wavelength at which these objects are having the maximum emission, it can be determined using the Wien's displacement law, which states that the relationship between the true temperature of a black body and its peak spectral excitance or the dominant wavelength, it can be described by this formula: lambda max is equal to k by T. Now this k is constant, having the value of 2898 micrometer Kelvin, and T is the temperature in degree Kelvin. So more is the temperature, will be having the dominating wavelength towards the shorter wavelength. For example, we considered the sun as a black body having the temperature of 6000 Kelvin and earth as a black body having the temperature of 300 Kelvin. So when we are having the 6000 Kelvin in the denominator part, the lambda max is towards the shorter wavelength, and because of this the solar radiation are the shortwave radiation. And when we are considering here 300 Kelvin in the denominator part, the lambda max is towards the longer wavelength, and because of this the emitted energy from the earth is considered as the long wave radiation. So, why this Wien's displacement law or knowing an object's dominant wavelength is important in the thermal infrared remote sensing? Because the dominant wavelength, it provides the valuable information regarding the part of the thermal infrared spectrum. Suppose if you have to study about the forest fire, which is having the temperature near to 800 Kelvin, so the energy which is emitted from the forest fire would be having the dominant wavelength approximately 3.62 micrometer. So for this, 3 to 5 micrometer thermal infrared detector will be suitable. But suppose if we have to study about the ambient temperature of the soil, water or the rock on the earth, which is having the approximate temperature of 300 Kelvin. So the thermal energy which is emitted from these objects will be having the dominant wavelength approximately 9.67 micrometer. So for these, the thermal infrared detector operating in 8 to 14 micrometer is suitable. As we saw in the starting of this video, that the radiant temperature is always less than the kinetic temperature of the object, and this mainly happens due to a thermal property called emissivity. So let us see what this emissivity is. In our surrounding, we do not have the perfect radiating black bodies, but we have the selectively radiating bodies such as the rock, soil, vegetation and water. So these emit only a certain proportion of the energy in comparison to the energy emitted from a black body at the same temperature. So this emissivity, it refers to the effectiveness of the surface in emitting the energy as the thermal radiation. सो जो हमने अभी स्टीफन बोल्ट्जमैन लॉ देखा था फॉर द ब्लैक बॉडी, वहाँ पे m इज इक्वल टू सिग्मा टी टू द पावर 4. But for the selectively radiating bodies, we include the emissivity factor here. So the Stephen Boltzmann law for the selectively radiating bodies is modified into this formula where the emissivity is also taken into account. If we represent the radiance emitted by a real world selective radiating bodies as the MR, and for a black body as MB, and we can rewrite formula like this and can define the emissivity as the ratio between the actual radiance emitted by a real world selective radiating body and the radiance emitted by a black body at the same kinetic temperature. Emissivity is a dimensionless number between 0 and 1. 0 is for a perfect reflector and 1 is for a perfect emitter. And all the selectively radiating bodies, they have the emissivity ranging from 0 to less than 1, and it fluctuates depending upon the wavelength of the energy being considered. As we can see in these two images, where on the y-axis we have the radiation intensity and on the x-axis we have the wavelength. For a black body, we are having the emission in all the wavelength ranges starting from 1 to 7 micrometer. But for the selective radiator, we can see the emission is only in these two wavelength range. We are not having the emission in these part. Similarly, in this graph, this curve is representing the emission from a black body and this curve is representing the emission from a real body. If we compare these two curves, we can see that the total emission from the real body is very less in comparison to the black body, and also it is for a selective wavelength range, and that is the reason that it is mentioned here that the emissivity for the selectively radiating bodies, it ranges from 0 to less than 1 and also fluctuate depending upon the wavelength. In between the black body and the selective radiator, we have a third curve which represents the gray body. So the gray body is having the constant emissivity value across all the wavelength range, but it will always be less than 1. As we can see in both the images, the gray body is having the emission pattern similar to the black body, but the amount of emission is less than the black body, as we can see here also. So any object which is having the constant emissivity across all the wavelength but less than 1, it is the gray body. Here we have the comparison of the thermal emission from a black body and the real world feature. In the first case we are having the water, in the second case we are having the granite, and in third case we are having the dunite. All are considered at the same temperature. On the y-axis, we have the radiant energy, and on the x-axis, we have the wavelength in all these graphs. So in the first case, we can see this bold line is representing the radiant energy from a black body, while the dotted line is representing the radiant energy from the water. Both are at the same temperature, but the total amount of emission from the water is less than the black body, and the emissivity value for the water is 0.98. In the second part, if we see for the granite having the temperature of 350 Kelvin, the radiant energy emitted for this particular wavelength range is similar to that of the black body. But for this wavelength range, we are having this dip, and across this wavelength range, we can see that the emission is less in comparison to the black body. And the emissivity value for this particular wavelength is 0.86 for the granite. Similarly, in the third case for the dunite, we can see that the thermal emission or the amount of radiant energy is less in comparison to the amount of radiation from the black body. And here we can see there is a large dip around the 10 micrometer wavelength range, and at this particular wavelength the emissivity of the dunite is 0.78. As per the law of conservation of energy, the radiation which is incident on the Earth's terrain will either get reflected or it will be absorbed or transmitted. So we can write that incident radiant flux is equal to radiant flux reflected plus radiant flux absorbed plus radiant flux transmitted. If we divide all these by the incident radiant flux, so we get spectral hemispherical incidence, which is equal to spectral hemispherical reflectance plus spectral hemispherical absorptance plus spectral hemispherical transmittance. According to the Kirchhoff's radiation law, in the infrared portion of the spectrum, the spectral emissivity of an object it generally equals its spectral absorptance, क्योंकि जो हमारा terrain है अर्थ का, it theoretically does not lose any incident energy to the transmittance. Means in this equation we can write zero here. Means जो भी incident energy है, that is either reflected or absorbed. So whatever is absorbed, that will be emitted. So all the energy which is leaving the object, it must be accounted for by the relationship between the reflectance and the emissivity. So as per the Kirchhoff's radiation law, good absorbers are good emitters and good reflectors are the poor emitters. Here we have the emissivity value for some of the materials, and if we compare for a same material, the one which is polished will be having the more reflectance. So this is having the less emissivity value in comparison to the unpolished or the anodized one. Similarly for the copper we can see the polished one is having the lesser emissivity value while the oxidized copper is having the more value. Water, it is a very good absorber of the electromagnetic radiation. So more is the absorption, more will be the emission of the energy. So we can see the emissivity value is 0.95. Similarly for the soil, if we compare, for the dry soil the emissivity value is less, while for the saturated soil it is more, because if it is having the water, there will be more absorption of the electromagnetic radiation and thus more emission. As we saw that the black body radiation principle for the real world materials, it can be modified into this formula by including the emissivity factor in the equation, and the thermal sensor can measure the radiant temperature of the object. So we have this relationship between the radiant temperature and the kinetic temperature, and if we know the radiant temperature, we can estimate the true kinetic temperature of the object if the emissivity of the object is known. Emissivity is important in thermal remote sensing because two objects on the ground having the same kinetic temperature can have the different apparent temperature or the radiant temperature when sensed by the thermal radiometer. And this emissivity is affected by many factors like the color of the object, because the dark colored object are the better absorber and better emitter in comparison to the light colored object. Chemical composition also affect the emissivity. Surface roughness, greater is the roughness, better is the emissivity. Moisture content can also affect the emissivity. More moisture, it will lead to more absorption of energy, thus more emission. Emissivity is also affected by the compaction of the material. Field of view means at what height this radiometer is placed. Whether we are measuring the radiant flux from a single leaf or from an entire canopy of a tree, the emissivity will vary. And also at which wavelength this emission is getting measured, that will affect the emissivity value. And the viewing angle of the instrument is also an important factor in affecting the emissivity. We will continue after this topic in the next video, covering the thermal properties of the terrain, thermal infrared data collection, thermal infrared environmental considerations, and the application of thermal infrared remote sensing. These are the references from where the content of this video have been taken. You can refer to this book, Remote Sensing of the Environment. There is a chapter, Thermal Infrared Remote Sensing. Majority of the content of this video have been taken from that particular chapter only. We will meet soon in the next video. Thank you and the best wishes.